Hello and welcome to today's class. Today we are going to discuss the potential due to a uniform solid sphere. So to consider this, we will first need to draw a sphere, and I'll try to draw it in 2D plane like this. And this is the center O. This is the outside point P at which we will be measuring the potential, and this sphere has a radius A. Okay. Now we have already calculated what is the potential for a hollow shell. Now all we need to do for this is we will find out the potential for the hollow spherical shell at point P, and then we will integrate that potential for the whole radius. So let us consider a hollow spherical shell first. This is the shell of thickness dr, and this has radius x and this is dx, and this is the distance r of the point at which we will be measuring the potential. So if the mass of this whole solid sphere is m, then we know the density of this sphere will be m by 4 by 3 pi a cube. It is 3m by 4 pi a cube. And now you can see that this area of this spherical shell is 4 pi a square, and to construct a volume element we need to multiply this volume area of this shell by its thickness, which is dx. So 4 pi a square dx we multiply, and now the mass of this spherical shell becomes rho dv equals 3m by 4 pi a cube into 4 pi a square dx. So if we multiply this 4 pi a square cancels out from numerator and denominator, and it becomes 3m by a dx. Sorry, we have I'm done a mistake here. This dv is not 4 pi a squared. This is 4 pi x squared dx. This radius is x, so this is 4 pi x squared dx, and 3m by a cube x squared dx. This will be, so this is the mass m dm, and we will find the potential dv is minus g dm by r. And we have seen for a hollow spherical shell that if the point is inside this shell, then the potential is equal at any point inside the shell, and that is minus gm by r, where r is equal to the radius of this shell. And when it is outside, it's equal minus gm by r, where r is equal to the distance between the center of that sphere and that point P. So we will write here dv equal to minus g dm by r for r greater than x, and dv equal to minus g dm by x for x greater than r, that is this point is this point is located inside this radius, this distance is r, and this is the radius x. So what I can do is I'll put the value of dm here, and it becomes dv equal to minus g by r 3m x square by a cube dx. So if r greater than x, we can just do v equal to integration dv, that becomes integration g dm by r, so minus g by r integration dm, that becomes minus gm by r. And if we find the potential that for outside point, we can do this integration minus g. Here dm is dependent on x, so we can write this value 3m by a cube x dx, so minus g 3m by a cube x square by 2, and the integration will be from 0 to x, so this will be the value actually 0 to r minus 3gm r square by 2a cube. No, sorry, I have again done a mistake here. So this is the formula for potential, that is inside, when the point is inside. But for a inside point, there is potential at that point due to two parts. That is, one is due to this inner part, this is inner spherical part, and there is this outer shell, due to which we will get a potential. So we will consider the potentials for at this point for those two parts separately, and then we will add them up. So first thing, at an inside point, suppose this is located at a distance x. Suppose this is located at a distance r. Then the potential at this point becomes minus g dm by r due to a unit spherical shell here. So, and we will find this dm by we have already found it, minus gm by r. So we will find the mass of this whole sphere as m by 4 by 3 pi a cube times 4 by 3 pi r cube. It is mr cube by a cube, so that becomes minus g by r mr cube by a cube minus g mr square by a cube. Okay, this is the potential due to the inner point, inner sphere, inner solid sphere. Now we will need to consider the potential at this point due to the whole outer spheres. Now we know an important thing, that wherever the point is located inside a spherical shell, its potential is just equal. Inside a spherical shell, the location of the point has no effect on the potential as long as it is inside. So we will need to find the potential inside for a spherical shell. So let me do that. Minus gm by minus g dm by x is the where x is this is the potential at the point P due to a spherical shell. Okay, now dm we have found previously is minus g by x into 3m by a cube x squared dx, so it becomes 3gm by a cube x dx. Now we can find the potential due to this whole spherical shell by integrating this elemental potential from r to the whole radius, that is a. So v becomes from r to a minus 3gm by a cube x dx, that becomes minus 3gm by 2a cube a square minus r square. So we will consider this potential as V2, that is the potential due to this shell, and this is the potential that is due to the inside sphere that I have written here. So ultimately the total potential becomes V1 plus V2 equal to minus gm r square by a cube minus 3gm by 2a cube a square minus r square, ultimately becomes 3 gm by 2a cube r square 2r square plus 3a square minus 3r square, ultimately that gives us gm by 2a cube 3a square minus r square. So we have found this. The potential due to at an outside point will be this, that minus gm by r, where m is the total mass and r is the distance. But at an inside point the potential will be minus gm by 2a cube 3a square minus r square. So I hope you understand this, and let us move on to the next topic.